This is lesson 2.3, Analyzing Rational Functions. In this lesson, the focus will be on determining the characteristics of graphs of these rational functions. So first, let's take a look at what a rational function is. A rational function has the form y is equal to f of x over g of x. So notice that we have a fraction here. That'll always happen in these rational functions, where f of x and g of x are polynomial functions and g of x cannot equal 0. Now I just want to focus on this part for a second here. You'll notice that whenever we have fractions like this, you might remember this from Pre-Calculus 11 because we did deal with rational functions. We had to deal with our non-permissible values. And so that's why we have this statement that g of x cannot be equal to 0. So that's going to be one of the things that we're going to have to watch out for is dealing with non-permissible values. What can x be and not be? In this lesson, I've broken it down into 3 characteristics that we're going to be looking at. And so we're not looking at specifically going and graphing these rational functions, but just finding out some information about them. And so one of the things that we're going to look at is how do we find those non-permissible values that I was just talking about. So let's take a look. If I give you the example y is equal to x plus 2 all over x minus 2 times x plus 1, my guess is most of you pretty quickly can find out what the non-permissible values are. All you do is you look at your denominator right here and you consider, are there any values that x could not be that would turn this into being 0? So we can probably see right here is if we put in a 2, 2 minus 2 would give you 0, and then 0 times whatever this is, it gives you 0, which would give you a division by 0, which you can't have. Same with this one, x cannot equal negative 1. So the first thing that I can tell from this first rational function right here is that my NPVs are that x cannot equal 2 and x cannot equal negative 1. Okay? Now, the next thing I want you to look at whenever you have a rational function right here is, are there any common factors? As an example, x plus 2 and x minus 2, can we cancel those? Well, no, it would have to be x plus 2 and x plus 2. If we could cancel those, for instance, this makes this question kind of entirely different. So the note that I'll make right here is that there are no common factors. Okay? And lastly then, because we have these NPVs right here at 2 and negative 1, let's talk about where our vertical asymptotes are going to be at. So the vertical asymptotes happen wherever those NPVs are located at. So we have vertical asymptotes at the values x equals 2 and x equals negative 1. So if you remember from grade 11 last year, Pre-Calc 11, we dealt with asymptotes. So you've likely seen those before. And this is where they would go. So if we have x equals 2, that makes a vertical dotted line, and it's going to be at 2 right here. Okay, so our function is going to get infinitely close to that line, but it'll never cross it. And then we're going to have another vertical asymptote right here at negative 1. Okay. So that's the only thing I really need you to know about this graph, just to kind of show you how these asymptotes work. The graph of the original function that we just had here, x plus 2 all over x minus 2 times x plus 1, would look something like the following. I'll do it here in green. Looks something like this, and that part would go like so. Noticing it's not crossing those asymptotes. It's bounded by those asymptotes. It would look something approximately like that. Again, that's just a very rough draft. But you can see how the asymptotes work into that function. Let's take a look at a different one. What if we had the function y is equal to x minus 3 all multiplied by x plus 1 all over x minus 3? Okay. So first of all, just like we did over here, let's start with my NPVs. That should be quick. In this case, as you can guess, x cannot equal 3. So again, just so that you remember, this will be a vertical asymptote right there. Let's take a look and see if we have any common factors. You'll notice that we do have a common factor. X minus 3 and x minus 3, those are both going to reduce. So we have a common factor. And when we have a common factor like that, we are left with a new equation. And when we get those common factors out of the way, we now have a new equation that looks like this. Y is equal to x plus 1. And when that happens, something funky happens compared to what we had with the function on the left-hand side. Wherever we have this NPV right here, it's going to make a hole in the graph. So there's going to be a hole in the graph at x equals 3. So we're not going to actually have a vertical asymptote like we first thought we were going to have right here. We're going to just have a hole. And if you take a look at this function right here, this y is equal to x plus 1, hopefully that function kind of rings a bell. That's just a straight line. So this function that we thought was going to be kind of a weird looking rational function where we're going to have asymptotes all over the place is not going to be quite as strange after all. So let's go and graph this. So what we'll have right here is we are going to have, if we take a look at the function, we have x plus 1. So I have my y-intercept at 1, so I'll put a dot right there. My slope is up 1 over 1, up 1 over 1, rise over run. And then when we get to this value when the x is equal to 3, we've got to be careful, because we cannot have x values equal to 3. So what we do to show that that point does not exist on this graph is we're just going to use an open dot like that. And then we'll continue on, like so. All right, and if we take our straight edge, you'll have a graph that looks something like the following. Okay, so just to review what we learned about on this page is that the first thing I want you to do whenever you have a rational function like this is I want you to consider what your NPVs are. So we found those right away. That was here and that was here. And then what I want you to consider is there any common factors? If there is, wherever that NPV was, that is going to create a hole, just like we saw in the function right here. Okay, let's go on to taking a look at an example. Example number 1 says consider whether the following functions have vertical asymptotes or holes. Well, what we'll do first is we'll factor this. So let's start with the one on the left-hand side here. This gives me y is equal to x plus 5 and x minus 5. Hopefully you recognize that this is a difference of squares right here. All right. So now that I've gotten that, let's talk about what my MPVs are. So we have an MPV such that x cannot equal -5. That would make that 0. So that we would think right now is going to make a vertical asymptote. But be careful. Notice that these are common factors. So I'll also make that as a note. We have a common factor. And the new equation that it makes is it makes the equation y is equal to x minus 5. So it said consider whether the following functions have a vertical asymptote or hole. Well, what we can say is that this graph is actually going to have, we'll just do it in green right here, we have a hole at -5. So again, this would be a linear function with this case does not have any asymptotes, it just has a hole. Okay, let's take a look at the one on this side. So again, I'll try to factor first. Why we're factoring is we're just trying to identify a little bit easier if there would be any common factors. And I think what you'll see in this case is we don't have any common factors. So therefore, we'll do the same thing over here. We know that my MPVs are at x cannot equal 2. There is no common factors. So we know that in this case, there's going to be a vertical asymptote at x is equal to 2. Okay, so that concludes looking at our first characteristics. That was focusing on vertical asymptotes and any holes that you might see. Okay, characteristic number 2 is dealing with horizontal asymptotes. Let's start by looking at the equation y is equal to -2 all over x plus 2. So let's first start with what we did before and let's identify my NPVs. So in this case, we'd say that x cannot equal -2, and so we would have a vertical asymptote at x equals -2. Okay, so now that we've done that, let's start identifying if we have any horizontal asymptotes. Well, horizontal asymptotes, what do we do for that? The first thing that we need to take a look at is we need to highlight the degree of the function. So the degree of the function is whatever power we have of the variable. So we'd say the degree of the denominator is 1, and since there is no x in the numerator, we say it is 0. So what we can say right here is that my numerator is less than the denominator. So next thing we want to look at is what happens to y right here as x gets bigger and bigger. So again, we're trying to look at the characteristics of this rational function. So as the absolute value of x, this arrow right here means approaches infinity, so as it gets bigger and bigger and bigger, what happens to y? Well, what we can say about y right here is, imagine if we put in a big number like 10. -2 divided by 10 plus 2 is -2 over 12. What if we put even a big number in, like 100? We'd have -2 over 102, 1,000, 1,002. What if we put 10,000? Well, you can see if you were to put that number in your calculator, that would be getting smaller and smaller. So as x gets closer and closer to infinity, we can say that y actually gets closer and closer to being 0. So because y is getting closer and closer to 0, what we can say is that we have a horizontal asymptote at y equals 0. Okay? So now that we've determined what our vertical asymptote was, remember where the vertical asymptote, that was this guy up here, and the horizontal asymptote was this one right here, let's go and take a look at what those would look like on the graph. So I'll do my asymptotes in pink right here. The horizontal one that we have would be a line going right across your x-axis, and the vertical one was at, where was that? It was at -2, so that would be approximately right here. Okay? And just to give you an idea what the function would look like right here, how those asymptotes come into play, is you would have a function that would look approximately like this. So it's bounded by those asymptotes. Okay? Let's look at another one over here. Notice for this question that the degree is going to be slightly different. Okay, so we're really going to be focusing in on the degree here. But first let's start with getting our NPVs, just like we did before. So my NPVs, once again, is x cannot equal, in this case, -1, which means you're going to have a vertical asymptote at x is equal to -1. All right, so that's going to make one of those nice little vertical lines. So let's talk about the degree. Well, what can we say about the degree here? Well, the degree in the numerator up here is the same as the denominator down here. So I'm going to write numerator equals denominator. When this is the case, then what we're going to do is we're going to try to see how many times the denominator actually goes into the numerator. So in order to do this, we're going to try to write this equation in a different way, because that's going to help us take a look at what happens to this function, just like we did over here, as x gets bigger and bigger and bigger. So to do this, we're going to use synthetic division. So we will divide. And in order to divide, what I'll do here is I'm going to take my divisor, which is x plus 1, and I just set it equal to 0, which gives me -1. I take the coefficients of my numerator, 2 and 4, and put them in here. I like to always write an arrow because I'm going to take this term and move it down. I put a plus here because we're going to add the terms, as you'll see, and I like to do that, if you recall, from Unit 1 for my remainder. So now that I brought down this 2 times -1 is -2. 4 plus a -2 gives me a remainder of 2. So now that we have all that, we can use that information to help us. We can write our equation or our function in a different way. We now can write the function as y is equal to, this is my quotient, so I write that first, my quotient, plus my remainder comes next, all divided by my divisor, x plus 1. And you might say, okay, well, how does that help me? Well, again, what I'm going to do is I'm going to reference what we had right over here. When x approaches infinity. All right, so I'll do this right below. As the absolute value of x approaches infinity, let's see what happens. So we're going to break this into two different parts. The 2, there's no x associated with it, so I'm just going to neglect it for a second. This part right here, as x gets bigger and bigger and bigger, notice that we're going to have 2 over a very big number. That gets closer and closer to 0. So I'll just write right here that that part is going to approach 0. So if that part is approaching 0, and then we just have the 2 right here, we can say that my horizontal asymptote is at y is equal to 2. So the reason it's at y is equal to 2 again is because as this part, the x value got bigger and bigger and bigger, it approached 0, and then we just simply had the 2 that's left over. So when we go and graph this function, again, I'm not really too concerned about the graph of the actual function, more so just the asymptotes. We have the horizontal asymptote at 2, that's the one that we just figured out. If I remember correctly, we had the vertical asymptote at -1, so that would go down right here. And just to give you an idea of what the function is going to look like, we're going to tackle this more in the sections to come. You'd have something that looks ballpark like so. Okay? So let's try an example. Example number 2 says, determine any non-permissible values for x, and where the graph of the function has a hole, a vertical asymptote, or horizontal asymptote. So the hole in the vertical asymptote, that's what we covered when we were looking at the first characteristic, and then horizontal asymptote is what we just dealt with. Just like any of the other questions, I'm going to start by trying to factor. Why am I factoring? I'm factoring really to see if there's going to be any common factors. Notice that in this case there's not any common factors, so we can rule out the fact that we won't have any holes. Okay. Now these NPVs, what can we say about my NPVs? I have NPVs at x cannot equal plus or minus 2 from here and here. So because that is saying that we have MPVs there, we know that we have vertical asymptotes. So let's answer the one part of the question. We have a vertical asymptote at x equals 2 and x equals negative 2. Okay? So that's one thing that we've done. So we've tackled that part right there. Now we need to deal with the horizontal asymptotes. If you remember how the horizontal asymptotes worked, we needed to tackle what was bigger, the numerator or the denominator. So if you take a look right here, you can clearly see that the denominator has a higher degree than the numerator. So we'll just write that down. The numerator is less than the denominator. So when that happens, what we can say is as the absolute value of x approaches infinity, we know that y is going to approach 0. All right. So what can we say from this? We now know that we have a horizontal asymptote that is located, or is the equation y equals 0. Okay, so we found our horizontal asymptotes, that was this guy right here. We found our vertical asymptote, and we determined that the graph did not have any holes in it. That brings us to characteristic 3, oblique asymptotes. So to start this question, let's take a look at a function. We'll deal with y is equal to x squared all over x plus 2. Okay. Right away, what I hope you might notice about this function is that when we talk about degree, the numerator, in this case, it's not less than, it's not equal to, it's actually greater than the denominator. So in the other examples that we've taken a look at, remember it has been less than, that was like the one we just tackled. We've dealt with ones that have been equal to. When it's greater than, we're still going to divide just like we've done before. So when we do our division right here, we're going to take our divisor, which is negative 2. All right. We're going to take the coefficients up here. So the coefficient of x squared is going to be a 1. Since there's no x value, we have 0. And since there's no constant, we have 0. I like to always put my remainder right there. I like to add personally, and then we drop down the 1. Okay. So once we've finished this division right here, we'll be able to write it in a different format, which will help us take a look at really what happens as x approaches infinity, just like we've done with all the ones before. So 1 times negative 2 is negative 2. If I add those terms together, I have negative 2. Negative 2 times negative 2 is 4, and 0 plus 4 gives you 4, like so. Okay. So from this shenanigans right here, we can go and write this function in a different form. So we will now have y is equal to, we start by taking our quotient. Our quotient is a 1 and a negative 2. That equates to being, this is my constant, that's my x term. So I have x minus 2, that's my quotient. Now I'll take my remainder. Remainder is plus 4. And I'll put that over my divisor, which, if you recall, was x plus 2. Okay? And again, right here, I'm going to divvy this question up into 2 separate parts. I want to look at the second part first. So, as x, the absolute value of x, approaches infinity, what's going to happen? Well, for this part right here, you'll notice that this is just kind of a linear function. For the other part right here, that we have a rational function. And we know that as this value gets bigger and bigger and bigger, you're going to have 4 over a very big number. So that means this part right here is going to approach 0. So if that part approaches 0, then all you're going to have left is this function. Well, what we can say then is as x gets bigger and bigger, approaches infinity, we know that y is going to approach x minus 2. So that makes this weird asymptote that we're talking about, an oblique asymptote, really just a diagonal asymptote. So we've dealt with horizontal, we've dealt with vertical asymptotes, and we're now going to have a oblique asymptote. So the one thing I neglected when we first started this question is that I probably should have dealt with the MPVs. So let's just do that now. MPVs, what do we got? X cannot equal negative 2, so that means we are going to have a vertical asymptote still at what's it going to be? X equals negative 2. So let's go and graph that right away, and then we'll focus more on the oblique asymptote that we have here. So negative 2 is going to give me the asymptote that looks like this. Okay. And then the interesting thing that we get from this is that we're going to get this oblique asymptote. So we're going to have a diagonal asymptote. This is just a linear function, so we have a y-intercept at negative 2, and then we have a slope of 1, so we're going to get something that looks like so. And because it's an asymptote here, you can probably get away without using a ruler. You're just going to have something that looks approximately like this. Okay. And so that's all we have. If you want to look at what this function would approximately be like, you would get something that looks like this, that's bounded by those asymptotes, like so and like so. Let's go and tackle our last example, and we'll be through with this lesson. So example 3 here says, determine any non-permissible values for x and where the graph this time has any holes, vertical asymptotes, horizontal asymptotes, or oblique asymptotes. That's what we just discussed. So let's start by again seeing if there's any holes. How do we see if there's any holes? We'll do that by first factoring. Okay. So factoring this, we have numbers that multiply to give me -3 that have a sum of 2 would be x plus 3. And a x minus 1 all over x plus 1. And so that work proved not to really help us a whole lot because we didn't have any common factors, so there's not going to be any holes. We don't need to worry about that. Let's go and make sure we've dealt with the vertical asymptotes right here. So we can say that we are going to have NPVs at x cannot equal -1. So that means, of course, that we're going to have a vertical asymptote at x equals -1. So we've dealt with a couple things we need to do. Now let's go and take a look at if we have a horizontal or a oblique asymptote. So to do this, we will do our synthetic division right here. So I will start by writing this out. My divisor is x plus 1, so I'll put a -1 sitting out here. I'll take my coefficients being a 1, a 2, and a -3. I like to put my remainder like so, and we are always adding. Bring down the 1. 1 times -1 is -1. 2 plus -1 gives you 1. 1 times -1 is -1. And if you add those two terms together, we have a remainder of -4. Okay. So what does this help us say? This helps us rewrite the function in a different light here. So we have y is equal to, we always start with your quotient, so this is my constant, that's my x term, so we have a quotient of x plus 1. We have a remainder of -4, so it's going to be minus 4 all over my divisor, which was x plus 1. Now from here, as you can probably imagine, this function right here and right here is going to be broken in two. I think you can probably see as the absolute value of x approaches infinity, this part right here is going to go to 0. So what we can say is that y is going to get closer and closer to being x plus 1. So because we have this, we now have again a, oops, not a horizontal asymptote, but we have a oblique asymptote. Okay, and I didn't put the graph on there just because we just finished graphing an oblique asymptote, but it'll look very similar. So to conclude this question, we had no hole to the graph. We found out that, of course, there was a vertical asymptote. That was at this point right here. There were no horizontal asymptotes, but we did have a oblique asymptote. Okay. So to conclude this lesson, the big ideas that we covered, the first thing you need to do is try to factor your function. When you factor your function, it does two things for you. It helps you find these MPVs and also helps you figure out if there is or is not a hole. So once you have your MPVs, of course, you know your vertical asymptotes. And then you just have to determine what the degree is. And the degree will tell you if you're going to have a horizontal asymptote or a vertical asymptote and where those asymptotes are going to be. All right? That concludes this lesson.